Breakwaters are structures constructed on coasts as part of coastal defense or to protect an anchorage from the effects of both weather and longshore drift. Purposes of breakwaters. Breakwaters reduce the intensity of wave action in inshore waters and thereby reduce coastal erosion or provide safe harborage. Breakwaters may also be small structures designed to protect a gently sloping beach and placed 1 to 300 feet offshore in relatively shallow water. An anchorage is only safe if ships anchored there are protected from the force of high winds and powerful waves by some large underwater barrier, which they can shelter behind. Natural harbors are formed by such barriers as headlands or reefs. Artificial harbors can be created with the help of breakwaters. Mobile harbors, such as the D-Day Mulberry harbors, were floated into position and acted as breakwaters. Some natural harbors, such as those in Plymouth Sound, Portland Harbor and Cherbourg, have been enhanced or extended by breakwaters made of rock. Unintended consequences. The dissipation of energy in relative calm water created in the lee of the breakwaters often encourage accretion of sediment. However, this can lead to excessive salient build-up, leading to tombolo formation, reducing longshore drift shoreward of the breakwaters. This trapping of sediment can cause adverse effects downdrift of the breakwaters, leading to beach sediment starvation and increased erosion. This may then lead to further engineering protection being needed downdrift of the breakwater development. Breakwaters are subject to damage and overtopping in severe storms events. Construction. Breakwaters can be constructed with one end linked to the shore, in which case they are usually classified as sea walls, otherwise they are positioned offshore from as little as 100 meters up to 300 to 600 meters from the original shoreline. There are two main types of offshore breakwater: single and multiple. Single, as the name suggests, means the breakwater consists of one unbroken barrier, which multiple breakwaters are positioned with gaps in between. Length of gap is largely governed by the interacting wavelengths. Breakwaters may be either fixed or floating, and impermeable or permeable to allow sediment transfer shoreward of the structures. The choice depending tidal range and water depth. They usually consist of large pieces of rock weighing up to 16 tons each, or rubble mound. Their design is influenced by the angle of wave approach and other environmental parameters. Breakwater construction can be either parallel or perpendicular to the coast, depending on the shoreline requirements. Types of breakwater structures. A breakwater structure is designed to absorb the energy of the waves that hit it, either by using mass, or by using a revetment slope. In coastal engineering, a revetment is a land-backed structure, whilst a breakwater is a sea-backed structure. Caisson breakwaters typically have vertical sides and are usually erected where it is desirable to berth one or more vessels on the inner face of the breakwater. They use the mass of the caisson and the fill within it to resist the overturning forces applied by waves hitting them. They are relatively expensive to construct in shallow water, but in deeper sites they can offer a significant saving over revetment breakwaters. Rubble mound breakwaters use structural voids to dissipate the wave energy. Rock or concrete armor units on the outside of the structure absorb most of the energy, while gravels or sands prevent the wave energies continuing through the breakwater core. The slopes of the revetment are typically between 1 to 1 and 1 to 2, depending upon the materials used. In shallow water, revetment breakwaters are usually relatively inexpensive. As water depth increases, the material requirements, and hence costs, increase significantly. Breakwater armor units. As design wave heights get larger, rubble mound breakwaters require larger armor units to resist the wave forces. These armor units can be formed of concrete or natural rock. The largest standard grading for rock armor units given in CIRIA 683, the Rock Manual, is 10 to 15 tons. Larger gradings may be available, but the ultimate size is limited in practice by the natural fracture properties of locally available rock. Shaped concrete armor units can be provided in up to approximately 40 tons, before they became vulnerable to damage under self-weight, wave impact and thermal cracking of the complex shapes during casting, curing. Where the very largest armor units are required for the most exposed locations in very deep water, armor units are most often formed of concrete cubes, which have been used up to 195 tons for the tip of the breakwater at Punta Langostera near La Coruña, Spain. Preliminary design of armor unit size is often undertaken using the Hudson equation, Van der Meer and more recently Vaingent et al. These methods are all described in CIRIA 683, the Rock Manual, the United States Army Corps of Engineers Shore Protection Manual and elsewhere. For detailed design, the use of scaled physical hydraulic models remains the most reliable method for predicting real-life behavior of these complex structures. Notable locations: UK, Seaporling, Norfolk, Elmer, West Sussex, USA, Santa Monica, California, Winthrop Beach, Massachusetts, Colonial Beach, Virginia, Japan, Central Breakwater in Tokyo, Ishizaki, Hokkaido Prefecture, Kaike, Tottori Prefecture,